Okay, so we'll start. What? Why is it not? The heck? Okay, so did yeah? Okay, so page 236. I'll pick and choose. Okay. Let's do 7. Take a look at 7. I would have you're gonna need this. I would have your data, your formula sheet out with turn to the back with the data on the back. You'll need that. You need the gravitational constants, the mass of the Earth. Okay. So give it a try. We'll go through it together.
Why do you radius? Radius for mass.
We're going to go over 7. Eight's easy. 9. 10. Do that, and we'll do 11 as well. So 7 and then 9 to 11. Start on those. I'll go over with you. For number 7, what I'd like you to do is do the calculation using, obviously, this is what the section's about. We've done this already, but just do a comparison. Do it again. Use that and use this. Do the calculation with both for number 7. Hey. Shh.
This is great, right? This is great. It's one gravitational force. Oh wait, never mind. That's force apart. Wait. Oh wait, no, it's because it's been attracted.
Yeah, and we know it's down. I'm more interested in the magnitude with this section here, but it is. FG is always down. So no, I mean, you can write this differently. I like writing it this way. You're going to see how it comes in handy in the next section. In some problems, there's a bigger central body. Actually, in most problems, there's a bigger body. In this case, the Earth. This is the Earth. This is the radius of the Earth. So I like distinguishing between the bigger and the smaller body. You'll see how that helps us later on. So I'm going to write it that way. But yes, you could just write M1, M2. And then someone help me with this. This should work out to be. What is that exactly? 690, I mean. Six. Yeah. So, yeah, exactly what we expected, right? It's the same. On the surface, this equation gives you the same, on the surface of the Earth, this equation gives you the same value as mg. This is only good, this equation is only good on the surface of the Earth, where g is equal to 9.81. This equation is general, universal, applicable anywhere on the surface or above it. Okay, 9. Freaking shit. Okay, so remember a couple of things here. First of all, the radius of the Earth. I'll just remind you of that. It says use the answer in 7. Reduce the number of calculations. Okay. Yeah, okay, I can do it that way. It's fine. I wanted to show you a different way though, but okay, so the new distance, what we're gonna have is that this is the way to do it. I'm gonna write FG new. Okay, this is FG new is equal to G. Same as above, right? Same as this, except it's a new distance. That's why it's new. Not the radius of the Earth. R new is the radius of the Earth. I'm gonna move it over. I'm gonna start. Plus the height that we're given here. So that is what we used here. That's the radius of the Earth. plus, still not enough room. Plus 6.38 times 10, so it's doubling it. Okay, this is supposed to be an H. So you're doubling the radius. This is I'm going to show you how to do it by just adding them, because you're not always going to have it as simple as doubling. So what do we get when we multiply this by 2? 6.38 times 10 to the 6. It is 1.276 times 10 to the 7 meters. That's our new. Okay. Okay. So what I'm going to be interested in is this. I'm going to put, this is a trick. I'm going to take our new, I'm going to divide it by just RG. Our FG is just this, just the old value. That's FG there. Okay, I'll plug it in later. It's 686. That's equal to okay, that's our new, that's FG new. And FG is just that's what FG is. I just wrote it. That's what FG is. I wrote it down earlier here in number 7. So look what's common on the right side here. What's common is this. GMM. GMM. That can cancel out. So be left with, on top, 1 over R new squared divided by 1 over R squared. Left side remains the same. Okay. So we can simplify this further. When you have a fraction, this is the same thing as when you're dividing by a fraction, it's the same thing as multiplying by its reciprocal. So that simplifies it. This is a trick that you're going to use in other problems, so a little long-winded, but have you got these? Let's just think about this. Yes. This is, go back here. We actually calculated 686. R is the radius of the Earth. So you got that, and R new, I calculated it up here. So you've got all your values. Okay, I calculated FG here. Radius of the Earth, 6.38. And the new radius, I know it's double, but it won't always be that simple, so we'll plug it in as a value. 1.276. Okay. So the new value works out to be 1.7. Times 10 to the 2. It ends up actually being a quarter of the old value, right? Try number 10 and 11. Try those out. Number 10, you can use this equation again.
I think they found an opening at the.
Sure.
So basically what I did is like, since you said like it's a quarter, so like.
Yeah, you won't. I know what you're going to do. You're going to use fractions, but that won't always work. Sometimes you'll be given numbers. So that's why I did the more general
You just
way.
have to find out like how much of that new number, how much it is worth of the previous number.
Yeah, that'll work. Yeah. But it's not always that. Sometimes you'll just be given some arbitrary number. So I went over the general. This should be 10 to the 7. It looks, is that 10 to the 6? That's 10 to the 6. It is 10 to the 6. Okay, we're just calculating the magnitude here. Yes, we know they're all down. Not your equation again. Comparing the new to the old. Number 11. Just read that over. Give that a try. Can I make a copy of this? I have to lasso it. Yeah, if we look at this problem, they're all the same mass. So we want to know, the question is, what is the force on this object here? On object 2. Due to 1 and 3. Okay. So what is the force? Here's the question. What's the force on 2? Okay, what's the net force on 2? That's the question. So what is the force being caused by? It's caused by 1 and 3. So you've got a force due to, this is the force the force on 2 due to 3. Notice I put the 2 first. The number that comes first is what's being acted on. The force is acting on 2. What's it due to? 3. And similarly, you've got an attractive force to the left. This is the force on 2. Whatever's being acted on, you put first. Whatever's doing the acting, the number comes last. So that's the force on 2 due to 1. Notice I drew those arrows the same length. And that's because the mass 1 and 3 are the same. And the distance is the same. Same distance. Same distance. Same force and magnitude, opposite direction. So they're going to cancel each other out. Zero. If one was bigger, let's say if F23 was bigger, I'd write the net force as F23 minus F21. If F23 was bigger. Okay? But they're the same, so they cancel each other out. You can just skip that step if you want. It's fine. Long as if you did this problem, as long as I said it in words, so you'd have to write it down. Just say F21 is equal to F23. I'd have to see that somewhere in magnitude. And then show me in the diagram they're opposite in direction, so they cancel out. Okay? Okay. It's a new topic. Let's see, what time is it? Good time, good. Gravitational field. Gravitational field. It's related to what we just did. Okay. So this refers to, you got, let's say, Earth. Earth is not, no, it's not an ellipse. There's Earth. And that's not good. Anyways, Europe's over here. Don't laugh at my drawings.
Uh-huh.
Yeah, I laughed myself. And I'm gonna color it blue here. Okay, no polar ice caps because they're disappearing. That's Earth. The field we're referring to is caused by gravity, and it protrudes outwards like rays of a sun. There's a reason for that. We'll go over that in a second here. Okay, and it's attractive in nature. So we're going to draw arrows inward, which means any mass in this field is attracted towards the Earth. Okay, we're going to call it, we're going to use the same symbol as we use for acceleration due to gravity because the value is the same. It's just expressed in a different way. The value or number is the same, but how we express it is slightly different. Gravitational field. It has units of not meters per second squared, although it's equal to meters per second squared, but it's equivalent to that, but the unit is newtons per kilogram. You'll see why it's equivalent. 1 Newton per kilogram is equal to 1 meter per second squared, so they are what we call equivalent units. Okay. It's defined as the amount of force acting on 1 kilogram. At a particular point in space. Okay, so what is that really? Essentially, it's just the acceleration due to gravity at different points in space, expressed instead of meters per second squared, expressed as newtons per kilogram. It's essentially the same thing. Okay, it's just expressed in a different unit. And what are the properties of it? Notice how I drew these little rays. They look like rays of sunlight. The fact that, notice the distance here between here and here is wider than the distance between here and here. The fact that these rays are spreading out is just a visual way of saying that this G, this acceleration due to gravity or gravitational field, decreases the farther away you get from Earth. Like rays of the sun. The rays of the sun weaken as you get farther away from the sun. Yeah.
Thinking. If you were to go to the moon,
Hmm?
if you were to go to the moon and feel there was a big aircraft, like a big station or something that was like half the size of the moon,
Right.
because you can't really do that on Earth.
Mm-hmm.
Would you feel the force of you being drawn to that big structure on the moon?
Yeah, if it was big enough. Has to be big enough. So it would have to be, if it's big enough in terms of mass, you'd feel it. So G, what is, again, how would we calculate G? Because G can change, right? Because FG can change. G is just, again, the acceleration due to gravity at different points, and it does change when you get farther and farther away. Why does it change as you get farther and farther away? Because G is just Fg divided by m, and this changes. Force of gravity decreases the farther away you get from Earth. And that's why the acceleration due to gravity or the gravitational field decreases. So we need a new formula. It's no longer 9.8 at a point far above the surface. How do we calculate it? From our equation for the force of gravity. That's your new equation for the acceleration due to gravity at any point, or the gravitational field strength. If the question is what's the acceleration? Acceleration, you already know, you'd give a value in meters per second squared. Apply the unit used is meters per second squared. If the question is what's the gravitational field strength? It's the same thing, same value. The only thing that changes, it's a different unit. It's expressed in terms of the amount of force acting on a kilogram. So the unit's newtons per kilogram. Same number. Yes, it is a vector. It's pointed towards the Earth. It's just another way of looking at the same thing. Acceleration expressed in terms of newtons. Yeah.
Gravity is just the force pulling down on basically nothing.
Gravitational field strength is the amount of force pulling down on a kilogram, on each kilogram.
Right.
Each kilogram is, let's say you're on the surface, instead of saying the acceleration is 9.81 meters per second squared, if you were asked a question, what's the gravitational field strength? You'd say it's 9.81 newtons per kilogram. What does that mean? It means every kilogram of your body is experiencing a force of 9.81.
And then it all builds up collectively.
Yeah, the more mass, obviously, the more force, yeah. I gotta go on.
Okay.
I have to move on. Yeah. So. Yeah. Let's just do a simple, these are pretty simple, right? But let's do one example. Okay, so on the Earth's surface, an object has a weight okay, that's its FG of 53.7. And the mass of 5.48. What's the magnitude? The magnitude of the gravitational field strength. On the surface, obviously. So what is G? That's the question. Just the magnitude. I know it's down. Just divide the weight by the mass. And you should get what we've been using, should work out to be close to 9.81. So 9.8. You wouldn't express it as, you wouldn't use this. That's the expression for gravity. Just change the unit. That's all there is to it. So unit here is newtons, unit here is kilograms. If you were calculating or asked the question, what's the acceleration unit, there would be meters per second squared. what unit you use depends upon what's the question. If you see that expression, use this unit. If it's acceleration, use this unit. Why are they equivalent? Because 1 Newton acting on 1 kilogram will accelerate that object at 1 meters per second squared. Okay, so there's questions on page 241, the handout that I gave you from last day. Try, what is the magnitude of gravitational on the planet X? Try 1 and 2. Let me see if you want to do 5 as well. Try 1, 2, and 5. One, 2, and 5. Sure. Go ahead. Yeah. Just looking at the doors open. 1, 2, and 5. Then you take a break. We'll just finish those. Oh, right. You don't like the red's okay. You don't like the blue. That's right. Should use a kind of a better red. Is that better? Pink's better? Okay, notice this value here for Mars is like almost 1/3 of the value on Earth. It's because Mars is a smaller planet. Its field is not as strong. I say 1, 2, yeah. Yeah, it's not going to work. I don't have enough room. Almost done here. I just divide, number 5, I'm dividing both sides, top equation by the bottom equation. So you're going to get this cancels out, this cancels out. You get G new, whatever the new value is of the field strength divided by the value on the surface, which is 9.81. Okay, and then as before, this here can simplify. Dividing by a fraction is the same thing as multiplying by the reciprocal. Okay, so we're told that the new field strength is a distance of twice the radius of the Earth. So this here is 2RE. You can do that if you want. Just plug in 2RE, that'll work. What is that? That's 9.81. That's the value on the surface. Squaring everything in brackets, you get 4RE squared. Okay, and then the RE squared cancels out. You just reduce it to 1/4. quarter of the old. Divide by 4. So that works out to be 2.45. What's the unit? We're not asked to calculate the acceleration. That's the right value for the acceleration. But what's the question? Yeah, the field strength. So use this unit. That's all the difference is. Just use a different unit. That is the force on 1 kilogram at that height. What's the acceleration? Same thing. Same value except meters per second squared. Okay, yeah, take a break. We'll come back and we'll work on some more problems.
That's the radius.
Right, so this is like the original, so it was at 7.33, right? So then, substitute this is basically times 2 now.